Well, in this lecture, we study properties of derivative. So, topic is properties of derivative. Properties of derivative. So, this is the main topic, and subtopics are following. We study derivative of constant functions. So, derivative of constant function or constant functions. So mainly, so basically we prove that derivative of constant function, so that is 0. So as in the function of a single variable. So there also we have seen derivative of constant function is 0. And next sub item is, so this is sub item 1, this is 2. So second sub item is derivative of linear transformations. So derivative of linear transformations. And third is, so we express derivative in terms of derivative of function. So derivative of function in terms of its component function, derivative of f. So that is function from, let's say, Rn to Rm. So here instead of Rn, you can take some open subset of Rn also. So derivative of f from Rn to Rm in terms of its component functions. And next, fourth item is, so derivative of some binary operations. So there are two basic binary operations, addition and multiplication. So derivative of s from R2 to R, where s is defined by s x comma y. This is equal to x plus y. This is sum function, and product function p, and p again this is also defined from R2 to R by px comma y. This is equal to x times y. And then we finished it by some corollary. So a corollary of the above. Okay, so let us start with the first item, derivative of constant functions. Derivative of constant functions. So let us state it as a theorem. So this is theorem 1. So derivative of constant function is 0. Derivative of a constant function is 0. So let f is a function from Rn to Rm be such that f of x, so constant function means f of x equal to some constant, so some fixed element b. So this happens for all x belongs to Rn, where b belongs to Rm. This is fixed. So this is constant function. So this proof of theory 1. And to show derivative of the function f at some point, let's say a, equal to 0. So for every a, this derivative is 0. So let us look at the following expression. So f a plus h minus f of a, and minus this is 0 function, 0 linear transformation acting on h. So o of, so 0 of h, this is 0, and divide by norm of h, so norm of the numerator. So this is equal to, so f of a plus h, this is equal to b, and f of a that is also equal to b minus 0. So norm of this over norm of h, and now numerator is norm of zeros, and that is equal to 0 by norm of h. So here h belongs to Rn minus 0. So, and this implies derivative of f at the point a equal to 0, and this happens for every a. So a is arbitrary, so this implies for all a belongs to Rn. So for all a belongs to Rn, derivative of f, constant function f, is equal to 0. Now we go to the second item, derivative of linear transformation. So second item, derivative of LT. So suppose t is from Rn to Rm. So recall that this function is called linear transformation if for all x comma y belongs to, so belong to Rn, and alpha comma beta scalars belongs to R, we have t alpha x plus beta y. This is equal to alpha times t acting on x plus beta times t acting on y. So this is the definition of a linear transformation. Now here the theorem is, so theorem 2. So if the statement is following, if t is linear from Rn to Rm is linear, then derivative of t at the point a, so for any a belongs to Rn, the derivative of t at a, this is equal to t itself. So for all a belongs to Rn. So well, proof of theorem 2 is following. So t a plus h, so h belongs to Rn minus 0 minus t of a minus t of h, so norm of this over norm of h this is equal to, so using the property of linear transformation, the definition of linear transformation, we have T acting on A plus H equal to T acting on A plus T acting on H, and minus TA minus TH. So numerator is equal to 0, so over norm H, and this is equal to 0 over norm H, and this is equal to 0. And this implies derivative of T at the point A, so this is equal to the linear part. So this is equal to T itself. Okay, so this is a proof of theorem 2. Now the third item. So the third item is derivative of function from f from Rn to Rm in terms of its component functions. So derivative of f from Rn to Rm in terms of the derivative of its means the functions f's component functions. So recall that, so f is a function from Rn to Rm, then x maps to f of x. So f of x, that is an element in Rm. So so f of x, that is m tuple. So right, this is equal to m tuple f1 of x and so on fm of x, where fi, this is real valued function on Rn to R. This is function for all I equal to 1 and so on m. Okay, so if i's are called the component function of f, so are called the component function of f. Of f. So now the theorem here is following. So basically we express derivative of f in terms of derivative of these component functions. So theorem number 3. So it says that if the function f from Rn to Rm, this is function, then f is differentiable at a belongs to Rn if and only if and only if each component function if I, so fi is from R, so real valued function on Rn, so Rn to R, each component function fi is differentiable at A. Okay, so for I equal to 1 and so on m. And furthermore, so we express the derivative of f in terms of derivatives of the component functions. So furthermore, the derivative of f df at the point A, this is equal to d1 f, so df1. So derivative of the component, first component function. So this is derivative of the first component function at A, comma. So this is linear from Rn to R. So this is the first component. So and d of derivative of f at A, that should be a linear function from Rn to Rm. So here we have m components. So and so on. Derivative of f m at A. Okay, so this is the derivative, and well, note that. So dfa, this is linear from Rn to Rm, and this is defined by, so theorem 3 says that this is defined by dfa acting on x. So here x belongs to the domain of df of A. So x belongs to Rn, and this is equal to df1 of A acting on x, and so on df m A acting on x. Okay, so and each these so these are reals, because if I, so derivative of the function if I at A, this is linear from R into R. So this is linear. Okay, so now we prove of theorem 3. So there are two parts. First we assume that component functions are differentiable. Then, so first we assume that component functions are differentiable. Then at A, then we show that the function f is differentiable at A. So assume that if I are differentiable at A for I equal to 1 to m, and define t equal to df1 at A, and so on dfm at A. Then to show dfa exists, to show that is f is differentiable at A, and that is equal to t. So this is what we need to show. So we start with the quantity f A plus h minus f of A minus t of h. And what is this? So this is equal to, so this is a very big expression. Let me write in the second line. So this is equal to the component wise, this is equal to f1a plus h minus f1a minus t of h has first component df1 at A, so minus df1 at A acting on h, and so this is the first component, and so on. The last component is f m a plus H minus Fm acting on A minus D Fm at A acting on H. Okay, so and now this implies norm of F A plus H minus F of A minus T acting on H. So norm of this is less or equal to so sum of absolute values of the components of the right hand side of this equation. So this is less or equal to summation I equal to 1 to m if I acting on A plus H minus if I acting on A minus derivative of the ith component function at A acting on H. So absolute value of this. So this is real number. So we have absolute value of this, and this implies. So let us go to the next page. So this implies norm of the left hand side f of A plus H minus f of A minus T acting on H, norm of this over norm of H, and so this is less or equal to summation over I equal to 1 to m limit H tends to, so here put limit H tends to 0, so this is less or equal to summation I equal to 1 to m limit H tends to 0, and the quantities are Fi A plus H minus Fi A minus dfi at A acting on H. So by the definition of derivative, so each of the limit on the right hand side is so this is norm of H. So this for each I, so this is equal to 0, so this is equal to 0, so the right hand side is equal to the right hand side is equal to 0, so this is equal to 0, and left hand side this is so greater than or equal to, so this quantity greater than or equal to 0, so this implies limit H tends to 0 norm of f A plus H minus f of A minus T acting on H, so norm of this over norm of H, this is equal to 0. So this is what we wanted to show. So this completes the first part. Now conversely, the converse part is easier. So conversely, so for the converse part, we use the following fact. So fact. So if you don't know this fact, consider this is an exercise. So we use the fact that the ith projection function from with domain Rm to R defined by, so recall the definition of pi I, so pi I x1 and so on x m, so this is m, so this is xm, so last component is xm, so this is equal to xi, and I lies between 1 and m. So this is projection function on ith projection function on Rm. So this is differentiable on Rm. That is pi I is differentiable at every point in Rm. So basically this fact follows from the second item. Okay, second item says that every linear transformation is differentiable and its derivative is itself the linear transformation. So here pi I is one can easily see that pi I is a linear function, and therefore it is differentiable and its derivative is pi I itself. So here we use pi I, and we have seen that if compose, so okay, so let me write in more precise way. So f is function from Rn to Rm, Rn to Rm, and here we have ith projection function pi I, and here we have f. So the composition function, this is pi I composed with f, and we know the ith component function of f, fi, this is equal to pi I composed with f, and therefore if f is differentiable, and from this fact pi I is also differentiable, so the composition pi I composed with f, this is differentiable from chain rule. So chain rule implies pi I composed with f is differentiable at a, when f is differentiable at a. So this completes the proof of theorem 3. Theorem 4. So this completes the proof of theorem 4. 4 or 3. Anyway. So this is 3. The fourth item is, so what is the fourth item? Derivative of sum and product functions. S Rn, so R2 to R, defined by S x plus y, this is equal to, so x comma y equal to, sorry, is x comma y, this is equal to x plus y. So this is simple. So theorem 5. Derivative of s at a comma, first of all, this is s is differentiable at every point a comma b in R2, and the derivative of s equal to itself. So proof s is linear. Now theorem 3. So now theorem 2. So this is about, so now theorem, what is theorem? So second item, theorem 2. So now theorem 2 implies theorem 5. So last theorem is 3. So this theorem is theorem 4. So this is proof of theorem 4. So now theorem 2 implies theorem 4. Okay, theorem 2 says that if T is a linear transformation, then T is differentiable and its derivative itself T. So, and here this is a special case basically, and theorem 5. So theorem 5 is so let P is a function from R2 to R defined by P x comma y. This is equal to x times y. Then P is differentiable and derivative of P at a comma b. So this is linear function from R2 to R, and then P is differentiable at every a comma b in R2, and the derivative of P at the point a comma b is given by dP at the point a comma b acting on x comma y. This is equal to b times x plus a times y. Okay. So from here, the matrix, so the Jacobian of P at the point a comma b. So let me go to the next page. So the Jacobian matrix P prime a comma b. This is basically B. So this is how 1 cross 2 matrix. So 1 row, 2 columns. Okay, so now we prove this theorem. Proof of theorem 5. So well, let T is linear transformation from R2 to. So here in the theorem we have hint the derivative of P at AB is given by this. So let us consider linear transformation T from R2 to R be defined by T x comma y. This is equal to B times x. So B times x plus plus A times y. So we can write A times y plus B times x. So then for A comma B belongs to R2, P of A comma B plus H comma K. So where H comma K belongs to R2 minus 0 comma 0 minus P A comma B minus T H comma K. So so norm of this, and this is absolute value. So this is equal to absolute value of P of A plus A comma B plus H comma K, that is P of A plus H comma B plus K, and that is equal to A plus H times B plus K. minus P of A comma B, that is equal to AB by definition of P, and minus T of H comma K, that is equal to B times H minus A times K. Absolute value of this, and this is equal to AB plus AK plus H times B plus H times K. And so this is equal to, let me write the full expression, AB plus AK plus BH plus HK minus AB minus this quantity minus AB minus BH minus AK, and absolute value of this. So everything will be cancelled out except this term H times K. So this is equal to mod H times K. Now this implies mod of P A comma B plus H comma K minus P A comma B minus T H comma K, absolute value of this over norm H comma K. This is equal to mod HK over norm H comma K. Now to show what to show now, to show that limit of the left hand side as H comma K tends to 0 is equal to 0. Therefore to show so that limit H comma K tends to 0, so right hand side has limit 0 as H comma K tends to 0s. So to show this equation holds true. Now so mod of H comma K, so mod of H comma K, that is less or equal to H square. So if mod H greater than or equal to mod K, and K square, so less or equal to K square if mod K is greater than or equal to mod H. And this implies, so in any case, this implies mod of H K, this is less or equal to H square plus K square. Therefore we have limit H comma K tends to 0 comma 0, so better to write 0 comma 0, so let me see, so here 0 comma 0. So limit H comma K tends to origin mod of H K over norm of H comma K, that is square root of is H square plus K square, and this is less or equal to, so this is non-negative, and this is okay, so this is non-negative, so and this is less or equal to H square plus K square over square root of H square plus K square, and limit H comma K tends to 0 comma 0, and this is equal to limit h comma k tends to 0 comma 0, and this is square root of h square plus k square, and this is equal to 0. So this is what we wanted to show. So this completes uh, the proof of theorem 5. So now we have a corollary of the theorems so far we have proved in this lecture. So corollary. So this is the last topic of today's lecture. So this is topic number 5. So this corollary is a very important corollary, and it has many applications. So, well, it says that if f and g are two real valued functions from Rn to R, so suppose these are differentiable at some point A in the domain of f and g, that is A belongs to Rn, then we have following. So this is first item. Derivative of f plus g at the point A is equal to derivative of the function f at the point A plus derivative of the function g at the point A. And the second item is derivative of f times g. So f times g at the point A, this is equal to functional value of g. So functional value of, so this is equal to functional value of g at A times the derivative of f at the point A plus the functional value of f at the point A times the derivative of g at the point A. And the third item is if at the point A g of A is not equal to, if this is not equal to 0, then f over g, this is well defined. So well defined in an open neighborhood of A, okay, by continuity of g at A, and derivative of this quotient function at the point A is given by the functional value of g at A times derivative of f at the point A minus functional value of f at the point A times derivative of g at the point A over the square of the functional value of g at A. So g of A square. Well, so the proof of the corollary. So, well, now let us define a function f from Rn to R2 by, so this is Rn. So this is Rn. So define by f of x equal to the ordered pair f of x comma g of x. Then by so this is by the fact that f and g, they are differentiable at a. So if so every component of capital F is differentiable at the point A, so f is also differentiable at A. So this exists, and derivative of this capital F at the point A is given by df at A comma dg at A. Okay, so now f plus g, so this can be written as s is some function from R2 to R, s of x comma y equal to x plus y. So some function plus f at x. So s compose f at x. So this is basically s of f of x. So f of x equal to f of x comma g of x, and this is equal to f of x plus g of x, and this is equal to f plus g of x. Okay, so not. So now from chain rule, so applying chain rule, we have derivative of f plus g at a. This is equal to derivative of s at the point f of a, and of derivative of f at the point a. So df at a, that is equal to df at a comma dg at a, and so this is equal to s itself because s is linear. So s of df at a comma dg at a, and this is equal to derivative of f at a plus derivative of g at a. So this is what corollary 1. So now proof of corollary 2. So here the proof is similar. So P is product. So P is product function from R2 to R. So P composed with f of x. So this is equal to P of fx comma g of x. This is equal to fx times gx, fx times gx, and this is equal to f times g of x. Therefore, what we have is f times g of x equal to p composed with f at x. So again, by applying chain rule, we have derivative of f times g at the point a. This is equal to, so here we are applying chain rule. So derivative of p at the point f of x, and f of x equal to f of a comma g of a, and derivative of then composite derivative of f at the point a, that is equal to derivative of f at point a comma derivative of small g at the point a. So derivative of g, okay, derivative of g at the point a, and this is equal to, so this is equal to g of a derivative of f at the point A plus functional value of f at the point A times derivative of g at the point A. So this is item number 2 in the corollary. So now the last item of the corollary, so the third item, the proof of corollary 3. Proof of corollary so well here f over g, so you can write so this is as p composed with f comma h composed with g, where h of x, so or h of t, not t is real, not equal to 0, so h of t equal to, so h of t equal to 1 over t, t not equal to 0. Okay, so again applying chain rule, we have derivative of f over g at the point A. So this is equal to derivative of p, derivative of p at the point f of a comma h composed with g of a, that is h of g of a, that is equal to 1 over g of a, and composed with derivative of the first component, derivative of f at the point a comma derivative of h composed with g at the point a, and that is equal to minus derivative of g at the point a over g of a square. And well, so this is equal to 1 over g of a times derivative of f at the point a minus f of a derivative of g at the point a over g of a square, and this is equal to derivative of f with at the point a and with coefficient g of a minus f of a times derivative of g at the point a over g of a square. Okay, so this completes the proof of corollary. So we stop here.